Okay, so we are already a few minutes late to start our colloquium. So without further ado, let me introduce our today's speaker, Professor Ziqian Wang from Boston College. So he got his PhD from Columbia and then was a postdoc at Rutgers and at Los Alamos National Laboratory. Then he moved to our paths, first as a faculty at Boston University, and since 1996 as a professor of physics at Boston College. Now, Professor Wang got multiple recognitions for his work, including fellowship in the American Physical Society, and he did outstanding work on very many topics, covering pretty much everything where there are interacting electrons, from heavy fermions to quantum magnets, to superconductors, to quantum Hall effect, absolutely everything you can think of. Now, this is not his first talk at Brown. The first time he came with a seminar in 1999, and now for us, of course, things change very gradually, and when we think what changed, say, over 10 years or even 20 years, it seems at the same place. As it turns out, when you compare with the perspective from 1999, everything is different, including even buildings. But what's very interesting, the subject of today's talk is surprisingly close to the subject of the talk in 1999, even though Professor Wang's works pretty much on everything. Both times, we got talks on strong interaction effects in superconductors. However, today, the talk is going to be even more interesting than in 1999, because among other things, we will learn about superconductors where instead of Cooper pairs, we have somehow groups of 6 electrons. So let us greet our speaker.
And yeah, 25 years ago I was here. A lot has changed to me, but I still have friends here, new friends. I'm very much enjoying conversations with everybody. So today I want to talk about Kagome metals and superconductors. So we work in quantum materials, many of us do, and what do we really do? We look for novel electronic states and novel excitations. And we need some help. We need sometimes strong correlation. The paradigm is high TC superconductor. Sometimes we need topology, therefore have fractional quantum Hall effect. More recently, we've been trying to get some help from geometry, from the geometry of the material in which the electrons are moving. So that's why I want to share with you some recent development in these Kagome materials. I want to at least try to convince you that there are some really interesting physics here that we don't completely understand, but they are really exciting. So what's a Kagome? Kagome is a pattern. It came from the bamboo baskets, as you can see here. I will make it simpler. These are corner-sharing triangles put together. These are motifs of molecular motifs, I would call them. Some of you know about the parachlor lattice, which are corner-sharing tetrahedrons. So it first came to physics in 1951 by this Japanese professor in Kyoto University. He was trying to follow Ansager's solution of the Ising model in 2D lattices. But now we know the most interesting thing is in the frustration. That is, if you have these triangles, then if you have antiferromagnetic correlations, you can make these two happy. You can never make the third one happy. But we know there is a way to solve this problem. That is to make the spins 120-degree oriented. But it turns out even that is not the only thing you can do, because once you have sort of non-collinear spins, then there are the scalar spin chirality that you can define, and I have different chiralities or vortices here for different configurations. So these fluctuation effects are huge, and this was really the center at the center stage in the 1980s, early 1980s. And it turns out if you have an ideal Kagome lattice, the spin just cannot even order. Even the 120-degree spin states can't even order. So what about Kagome materials? Now we leave StatMac Now, what about if we make a material using transition metals and have these transition metals occupy the vertices of these triangles? Then we have a perfect, as I drew here, Kagome lattice. And you see there are some other atoms here in the middle of the hexagon. They need to be there. The reason is the Kagome lattice is too empty. You need something in the middle so that you make them stable structurally. And then things will become really interesting, because when electrons move on this lattice, the energy momentum relation show what's called flat band, which can be topological. And you know that if you have a flat band, kinetic energy is quenched, then correlation effects becomes really strong. And there are these Dirac points, and these are topological points where dispersion is linear. And there are also these Van Hoff singularities. This band structure looks very simple, but it actually has a lot of really intriguing properties. So if we could do that, then what we have a basket. I call it a basket. And out of the basket, you have a lot of novel correlated and topological states. That's going to be what I'm trying to convince you today. So I have many collaborators. My colleague at Boston College, Ilya Zakovich's group. The work started with the collaboration with Zahid Hassan at Princeton. We have close collaborations with Hongjun Gao at IOP, the Chinese Academy of Sciences, and Xinjiang Zhou. Those who worked on high-TC cuprates know his RPES studies has made a real big difference. Stephen Wilson, Brandon Ortiz, they are the original discoverers of the material at UC Santa Barbara. Ricardo Coming, RPES person at MIT. Joe Tchaikovsky, sample grower at MIT. And more recently, I'll show you some of the data from Vidya Madhavan's group at Urbana-Champaign. And I also collaborate with Jian Wang from Peking University. This is on the 6e stuff that Dima mentioned. I don't know how much time I have to go into that, but I'll try. On the theory side, Binghai Yan from Weizmann, Chandra Varma, who is retired, but is happily traveling, spending his time between UC Berkeley and New York City. And Rafael Fernandez, Leon Balance, and some of my students and postdocs. And this is Jiangping Hu at IOP that we collaborate a lot on. So, okay, so that's my introduction, but it's hardly complete. So let me begin by telling you a trilogy, because those of us who love Star Wars can never get around with not talking about the trilogy. So the Kagome material study really has a trilogy. And the first part began with materials on the Mott insulating side. So these are insulators. They're called Herbert-Schmidtides. And they thought to be ideal materials for realizing a quantum spin liquid, for example, described by some maybe even more complicated Heisenberg-like models like this. The interest was fractionalized spin excitations and doped Mott insulators, whether you can get really a high-temperature superconductor from that. This was about 17 years ago, when the first work came about. Then about 7 years ago, people realized, hey, the metallic side might be equally interesting, just what I was alluding to you. Then I can explore this band structure. I can have different filling fractions of the material, so I can probe different kinds of physics. So the initial materials people looked at some of them were just old materials. People didn't realize they're actually interesting because of the topological aspects. For example, the cobalt tin sulfur is actually a magnetic well semi-metal. Ion tin and terbium manganese tin, these are close to a ferromagnetism introduced the Chern insulator or quantum anomalous Hall state, and many of these. But because these are all magnetic, right, the system never really goes into a superconducting state. So superconductivity was never found in these materials. Then about how many? This is just the beginning of COVID, so 5 years ago, a new class of vanadium-based Kagome materials were discovered. And now these materials are non-magnetic, right? So they're non-magnetic. And then they become superconductor at very low temperatures. But it's more complicated than that because there's still plenty of correlation. They first turn into a CDW, a charge density wave ordered state. Then they become superconductor. In fact, there is a cascade of symmetry breaking and correlated states exhibited by these materials. So that's, I think, is a fair introduction of the three trilogy of the Kagome materials. What's really impressive is it covers the entire spectrum of correlation, from very strongly correlated to this which you thought on the atomic scale that I'll try to convince you, not strongly correlated, but still shows many interesting correlation effects. And also covers the entire spectrum of topology. You have long-range entangled topological ordered states, such as spin liquid, all the way to these short-range ordered topological states. So that seems to be a really great playground. So how is this material discovered? I have them here, vanadium-based, 3 of them because you can change the alkaline metals. The vanadium forms these perfect Kagome lattice. In the plane, you have antimony here to make it stable. Then the antimony is also above and below these triangles, right? They form their own honeycomb lattice, and then sandwiched by alkaline metals. How was it discovered? They were not looking for this. They were looking for Zintel antimonite thermoelectrics, right? They just stumbled upon this, and I asked them, is this material good for thermoelectric? They said, no, not by a long shot, but it's very good for studying quantum physics. Okay, so 3 materials, right? KVS, RVS, and CVS, and they behave more or less the same. So what happens here is they all undergo a CDW transition as you lower the temperature, around 100 Kelvin. And what's really interesting is this is magnetic susceptibility. And above the CDW transition is paramagnetic. So there are no local moment or not even very strong spin fluctuations, right? And then they go through a CDW transition. This is the heat capacity. This is the resistivity. There's about 600 anisotropy ratio of resistivities in plane and outer plane. And at low temperatures, they all become superconductors. This is Meissner effect, our resistance versus temperature. Notice there is a broad transition region here already in these materials in the bulk, and this is the heat capacity. Transition temperature around 2 Kelvin. Okay, so now let's take study quantum materials. Usually what we do is we look at the band structure. We want to ask, is there anything special from these band structures? All 3 materials share the same band structure, very, very close to one another. And if I ask you, does this band structure look like a Kagome lattice? Does it remind you of these 3 bands that I drew for you? Yes and no. First of all, it's a multi-orbital system, very complicated. But if you look at this red one, it does show this feature. Quite flat here, Van Hoff singularities here and there. There's a Dirac crossing at the K point. And that's what we can hold on to. It is a Kagome material. The Fermi surface looks like you got a pocket in the middle. That comes from the antimony PZ orbital. That's probably boring. Most of the d orbitals are active near the zone boundary. But indeed, the Fermi level is quite close to the Van Hoff singularity. That's a landmark of these materials. The Fermi surfaces are given here. And all of these, instead of going into details, I'll say all of these DFT calculations are in overall agreement with the experiment, such as angle-resolved photoemission. Right? You find nothing really unusual. And more recently, well, actually, this was confirmed. It was first done in 2021. You do DFT plus DMFT. That is, you want to treat strong correlation due to Hubbard-like interactions. And you find the U is not very large. Right? The mass renormalization 1.3 is weakly correlated. There is no local moment. This was also seen in mu-SR data. There is no local magnetic moment or fluctuations. So pretty boring. Right? It's a CDW superconductor. We can say CDW transition here, superconducting transition here. But it turns out everything in between is anomalous or interesting. First of all, there is giant anomalous Hall effect, anomalous Nernst effect, right? And then the CDW state is seen to exhibit some sort of a handedness, and that can be flipped by magnetic field. I'll explain with detailed experiments. And time irreversible symmetry seems to be broken in this charge density wave ordered state. There is whole other phenomena related to rotation symmetry breaking. it turns out the six-fold symmetry of this hexagonal material is broken, and there is unidirectional charge stripe ordering, and there is also electronic pneumaticity at very low temperatures. Many of the high TC phenomenology you'll see here as well. So if the normal state is so anomalous, you know the superconducting state is going to be very strange or very interesting. First of all, the superconductivity coexists with charge density wave order. It's a many-orbital or many-band or multi-band superconductor. But more interestingly, the superconducting state exhibits a kind of pair density wave order. That is, the Cooper pairs seems to carry a non-zero center of mass momentum. Right? And there are pseudo-gap phenomena also both above superconducting transition and at low temperature with the field that is above the critical field for the superconductor. So in both cases, you still see pseudo-gaps remaining outside the superconducting state. And then there is this really anomalous phenomena or exciting phenomena that is the higher charge superconductivity detected by higher charge flux quantization. This is more recently, there are some experiments looking into the diode effect, and they concluded that the superconductor breaks time reversal symmetry as well, and probably a chiral superconductor. So I want to call these extraordinary superconductors, because I can't use unconventional superconductors anymore, because that is sort of reserved for superconductors that has that was there because of electron-electron interaction rather than phonon-mediated superconductor. I should say there is no evidence so far that points to this superconductor to be, non-electron phonon driven, right? But all the phenomena, all the quantum phenomena can be just as interesting as extraordinary. So I'll begin. I have no time to go through all of this, so I'll concentrate on time reversal symmetry breaking in the normal state, in the CDW state. And then I'll talk about what consequences this time reversal symmetry breaking might have in the superconducting state. But that is already a big challenge. The material, the field has grown so much, and there's so much interesting things to study. So let me begin with the first experiment that hint at there is something that might show time reversal symmetry breaking. So this is STM, right? And if you go above the CDW transition, this guy has a CDW transition, potassium one, of 80 Kelvin. So you go above that, and you look at the topography of the surface, and you see it's like this. You do a Fourier transform, it shows 6 Bragg peaks, nothing else. We know this is a great crystal, and we know what to expect from that. But if you go to lower temperatures, then there are additional Bragg peaks emerging. That shows there are additional structures in this material, and these peaks sit at half of the Bragg wave vector. So this is a sort of a 2A naught by 2A naught, 2 by 2 ordering, 3Q ordering of the charge density wave state. You see that in the DIDV maps, which are density of states maps, right? And you look at the DIDV as a function of bias, you see this is above the CDW transition. And when you go below the CDW transition, there is a CDW gap on the order of 50 millieV that opens up. Great consistency between scattering experiments and RPES experiment. Right? 3Q, 2 by 2 in-plane period. I should say there is actually an ordering wave vector in the third direction as well. It's 2 by 2 by 2. And Vesna has done NMR recently to give a microscopic picture of what the CDW's phase look like. I'll comment on that later. All right, so this is not surprising. What's surprising is we took a closer look at these CDW peaks, the 6 peaks in the Fourier transform that is at half of the Bragg wave vector. That says there is additional translation symmetry breaking, charge density wave order. Turns out they have all different heights. Now, 2 of them should have the same, across the center should have the same height. That was given by just the nature of STM to spectroscopy and Fourier transform. So you always have sort of a three C2 axis. But reflection, all reflections are broken. You can do a reflection along any of these 3 axes, that's broken. If all reflections are not there, you have a handedness. So in this case, if you go from weak to intermediate to strong, left-handed. right? There is a left-handedness in the intensity of the CDW peaks. We don't know what that means. It's never been talked about in physics, what this intensity difference would mean. But that's something unusual. So we thought maybe, could that be something that we can use to say it breaks time reversal symmetry? And the answer is no, because I can have a structure that breaks all reflection, and it will be chiral structure. So we apply a magnetic field, then something is really interesting. You apply a field in one direction plus 2 Tesla pointing upward, and there is one kind of chirality. When you flip the field direction to pointing down, the chirality changes, become right-handed. So you go from weak peak to intermediate to strong peak. So it is that chirality or that sense of handedness gets flipped by magnetic field, tells us, this state might be broken time reversal symmetry. And you have no magnetism. What can you say about what happened that break time reversal symmetry? So we conjectured, in the absence of magnetism, maybe the CDW state has a very exotic ordering, that is the current. There is persistent current that orders in the CDW state. Right? So it's circulating loop current order. So that was a proposal, and many people tried to repeat this experiment. You get people who can repeat it, people who cannot repeat it, including my own colleague, Ilya Zakovich's group. They took the same sample and did this experiment, didn't see this. Right? And also, it's just not so clear. What does it mean to have these peaks of different height? Right? Well, in between, a lot of the experiments that probe directly time reversal symmetry breaking, such as optical Kerr rotation, circular dichroism, some of them sees, obviously time reversal symmetry is broken. Some would conclude, no, they didn't see any signal. So the field is pretty much at the impasse. We don't know exactly, why this happens. It's not a yes or no question. So I often talk to people and they say, they didn't see it, so it's not there. But it's not a yes or no question. It is really a question about what happened. Yes, yeah. Yeah. Yeah, exactly. So, excellent question. So I'm going to. No, STM doesn't. This is all the evidence are here. These are the initial evidence. Something unusual has happened. Right. STM is not probing time reversal symmetry breaking. So what exactly is happening? Now, this was settled, or in my view, big progress was made by Vidya Madhavan. The paper was posted and it's under review. Let me explain this because it's such a beautiful story. I want to take all the time to explain this. Vidya has always thought she wants to study pump and probe, but not of the the pumped state transport behavior, things like that. She wants to probe the order parameter, right? So she wants to bring light between the surface and the STM tip, right? Laser coming in. And so she said, okay, I can do something on these Kagome materials. So this light comes in, the polarization direction of the light she can control, right? And that polarization can be can be along one of these crystal axes, these two directions, where you see these peaks are of different height. You can ask, what about this one? She's going to avoid this because this material, rubidium vanadium antimony, has this stripe ordering along this direction. So this direction is already very special. Let's leave that out. But she's going to probe these two directions, right? So this is what her experiment showed. The first one is without light, right? Without shining light. And she observes what the Princeton group observed. There is a sense of handedness in the peaks of the CDW intensity. Okay. Now she can shine light along the weak direction. For example, this direction is weak. So she can shine laser, retract the tip, put the beam in with the polarization direction that line in this direction, and then switch off the laser and push the STM tip down. Now the intensity is reversed, or the sense of chirality is reversed. Then she can go back and put, again, the polarization direction along now the weaker direction, and she'll flip the chirality again. So this optical flipping, switching of the chirality is essentially what she finds. And she can do this like that. It's almost like never fails. The chirality changes. And I asked her, how long can you keep this state there? She says she can go home and come back next day, do the measurement, that's still there. All right. So that's basically what she observed. And it still doesn't say anything because what is the order parameter? She's still using the height, the intensity difference. Of course, now she can control optically the intensity difference. Okay. So I said, let's try to find out what is exactly ordered. Can you actually see the Bragg peak location? She says she can. So these are very high resolution STM measurement, and she can really see the light-induced anisotropic lattice strain. So these are now just the Bragg peaks. This is not even the CDW peak. You look at the 6 Bragg peaks, right? And you blow it up. This is where it's supposed to be the red dot, right? If everything is isotropic and perfect, right? But no, right? This peak intensity these are the 4 pixels. You look at the center of gravity is here. For this peak is here. So this Bragg peaks never sits at where it's supposed to be. Okay, now when she changes, when she shines laser with a polarization along Q3, where is Q3? Q3 is this, right? You see, she can change basically the lattice constant so that the Bragg peak shifts in this direction, expands, and in the other direction, contract and goes in. Right? What is this? This is actually a nonlinear effect of electric field-induced lattice strain or lattice distortion. That's electric striction. So it is the electric striction that is being used to manipulate this chirality, or the chirality is a result of anisotropic strain. This peak intensity of different heights is a reflection of actually the lattice has a shear strain applied onto it. So now this can be in one-to-one correlation with what she observes here, whether the lattice expands or contracts in that direction. So in summary, if the field is along this direction, the Q becomes bigger, so the lattice constant becomes smaller in this direction, and in the other direction, it does the opposite. All right? So that is a great progress. At least we know what is really changing. It is indeed the lattice become chiral, if you wish. There is that chirality is a reflection of the lattice strain. Right? So it's strong electron-phonon coupling, or zone boundary phonon coupling that leads to this. This doesn't say anything about time irreversible symmetry breaking. So we thought we just need to apply the field and see if we can switch the chirality together with the lattice strain. If that's the case, then we have really insight into this. Yeah?
So the persistent curve loop idea goes away?
No. We don't know. No. Look at the next one. That's exactly the next page. This is where I will answer Vesna's question. Is there a magnetic field-induced strain? Of course there is. It's called magnetostriction. But it's actually subtle. So I've just roughly written down, this is the strain tensor, and its response to some stress, and then magnetic field. This is the usual term of magnetostriction. It's quadratic in magnetic field. It doesn't break time irreversible symmetry. But in 1951, Zaluzhinsky noted that there could be a linear term in magnetic field. And this term is called piezomagnetic response. And the coefficient is the piezomagnetic tensor. If this tensor is non-zero, then the system breaks spontaneously time reversal symmetry. So then magnetic field in one direction versus the other direction will cause different shear strain or lattice distortion. And that would be the way to probe time reversal symmetry breaking. And indeed, she finds that this is a 2 Tesla field in the minus direction or plus direction. You see that the lattice responds exactly in the opposite direction. And that says this term is non-zero. Okay? And this can be repeated by different field directions. You also switch this sense of handedness, right? And, well, maybe it's illustrated here. If BZ is greater than 0, these 2 ends go in, these 2 sides go out, right? So, really, what is happening is system breaks time reversal symmetry spontaneously. And using piezomagnetic effect, right? If that breaks time reversal, this is non-zero. So you can use a field to probe this piezomagnetic effect, and that causes the chirality flipping. So spontaneous time reversal symmetry breaking. I have not put in, we can actually have a loop current pattern that is consistent with these observations. All right? So what happens is if you break, if time reversal is broken and there is a shear strain on the system, you also break certain mirror symmetries, and that allows a net orbital moment to be produced. And that net orbital moment will couple to the magnetic field. All right? So that's, I'm glad I'm giving this talk because half a year ago, I would not have this part, and everybody was questioning why there is time reversal symmetry breaking. Okay, so that gives me now some justification to turn into a plausible theoretical picture for what might be happening. That would be the second half of what I'm going to be talking about. The loop current state looks like this. So the proposal is the time reversal symmetry breaking CDW state is a state in which there is an order of persistent loop currents. I just drew one like that. And because you're on the Kagome lattice, I'll show you time reversal symmetry breaking leads to a topological state. And that is a Chern insulator, but doped with some carriers, so it's called the Chern metal. And what you see here is this Chern metal has what's called Chern Fermi pockets, Fermi surfaces, and that exactly coincides with where the Berry curvature concentrates. So it can explain this anomalous Hall effect through the orbital magnetic moment. Then I'll talk about what's going to happen to these loop currents once you go to the superconducting state. And these loop currents it has to turn into loop supercurrents in the superconducting state. And the supercurrents must go around vortices or antivortices. So this will be a state of spontaneously nucleated vortex-antivortex lattice. And once you have a lattice, it carries a momentum, and that's what the Roton PDW pair density wave is all about. And there is a pseudogap phase coming out of vestigial order when you try to melt such a superconducting state. And I'll hopefully have time to talk about higher charge superconductivity that emerged from this picture. Okay, so I'm going into theory. Now, first thing is, can you explain the CDW? Turns out it's very easy. The Kagome lattice is really, really not a very stable structure. So the pristine Kagome lattice is never stable because if you calculate the phonon spectrum out of this lattice, you see it's at negative frequencies and at this zone boundary, M and L point. So the phonons are not stable, right? The structure is not stable. And these modes, these zone boundary modes corresponds to breathing of the lattice. It wants to breathe, either in or out. And there are two modes. Either you breathe in, you form what's called the star-David pattern. So the bonds are strong on these star-David links. Or what's called inverse star-David or trihexagonal, in which it breathes out. So you form these hexagons and triangles. I like to call them star-David, inverse star-David, just so that we know that they are actually just a pi phase shifted breathing, right? It's not a new structure. And you calculate the energy in DFT as a function of this lattice distortion, you find the inverse star-David is always lowering energy. So you might be concluding, CDW state can come from electron-phonon coupling. I mean, there are electron contributions as well, but the driving force, in my view, is electron-phonon interaction. And this can account for 2x2x2 CDW, but there is no time reversal symmetry breaking. So to talk about time reversal symmetry breaking, I must go into effective theories and looking at simplified models. So here is the simplest possible model that I wish all the students could actually work on your own. Right? There is a Kagome lattice. I'm putting one atomic orbital on this Kagome lattice. The Kagome lattice has three sublattices, 1, 2, and 3, marked in colors. So therefore, you have three bands, right? 3 sublattice, 3 band. And they look like this. I've shown this a number of times. And these are the eigenvalues of this matrix, hopping matrix, written in the basis of 1, 2, and 3 sites. Okay? We all know how to do that. We hope we all know how to do that. What's really interesting is the material is close to this Van Hoff point. Right? I showed you the DFT calculation. Very close to this. So let's just ask what happens here at these M points. Okay? I'm going to put the M point momentum in this hopping Hamiltonian. And let's ask, the Hamiltonian becomes so simple. Everywhere is 0 except these 2. Okay? So there are 3 eigenvalues, and look at the 3. The first one is this. This is a anti-bounding orbital, sits at 2T energy right here. And it's a mixing of sublattice 1 and sublattice 3. Very good, usual state. Okay, where is the bounding? The bounding is this Van Hoff point. It's a bounding orbital, 1 and 3 mixed. There is actually a non-bounding orbital at 0 energy. And its wave function is 0, 1, 0, so it's localized only on the second sublattice, which is the blue. All right. So this is really the special property. Beyond geometric frustration, the Kagome lattice has a sublattice polarization property. That is really, really interesting. So it says, if I'm exactly at the Van Hoff filling, I have this as the Fermi surface. And this Van Hoff point, all the electrons are localized on sublattice 1, the red spot. This Van Hoff point, all of them are on blue, as we just shown. And this one, all of them on green. Okay. So now things is becoming really interesting. If I want to take advantage of this Van Hoff singularity, high density of states, I want to, this is all nested. I want to use this nesting vector. I'm going to have to use 2 different sublattices, right? Which, for example, 1 and 2. And that's a bound. And this is the reason the charge density wave state on the Kagome lattice is most likely a bound-ordered charge density wave. It's not just side charge density wave. If it's side charge density wave, there's no chance to make a loop current. Now, if it's unbound, I can now make a loop current. So let me explain. I'm going to write down what will be the CDW state using this nesting, the 3 nesting wave vector here, right? That nests the Van Hoff point. So what do? We can write it down. CDW Hamiltonian, modulation by a cosine function using these Q, and the bound distortion. That's it. With an amplitude, rho of gamma. CDW Hamiltonian. Now, what are these density wave states? If this rho is greater than 0, I have Star of David, 1 distortion. If the rho is less than 0, I have the inverse Star of David, the other distortion pattern. Now, if this rho is complex, why not? Because it's unbound, it can be complex. Once it's complex, I have both bound distortions and current on the bound. And that's the loop current state. You can't really try to tell or speak of Star of David or inverse Star of David because look at this guy. I've chosen a positive real part and some imaginary part. The real part gives you a Star of David pattern, but the imaginary part looks like a inverse Star of David pattern. I have another additional knob that I can tune to minimize energy. So let me put these states here. This is the loop current state. It has a 2x2 unit cell in the plane. And really, the only gauge invariant quantity is the flux that you accumulate when current goes around a closed circle. The total flux is 0. You know this is kind of a staggered pattern. There's no net flux. Breaks time reversal symmetry. Breaks all reflections, but maintains inversion because that's a product of 2 mirror. So that inversion is still there. So it's an orbital antiferromagnet. Now, this has been this state, right, has been proposed a long time ago. I think the first person or persons who proposed this was Brad, 1988, with Jan Affleck. They proposed this for the Heisenberg model. This is in the context of high TC. There, the current is not necessarily electric current, so it's really the flux that actually is important. This is called pi flux phase. And later on, people looked at what happens if there are holes doped into the system and they have some electric current circulating, which is called staggered flux phase. It also undergoes the name of d-density waves. It's another way of writing this order parameter proposed by these gentlemen. And people have heard of loop current in the context of HEC. And in that case, it's a loop current going between oxygen and copper, right? And there is another mode I didn't draw here. It's Chandra-Varma's loop current state for the pseudogap phase of the cuprates. Now, we're going to call it loop current just because the name is simple, right? But it's all of these. It's an orbital antiferromagnet. The most interesting thing is this. This was also 1988. Brad, I don't know if you guys were aware of this paper in 1988. When Duncan Haldane proposed this phase, which is now known as the phase of quantum anomalous Hall effect, he also had loop current, all right, between the next nearest neighbors on the honeycomb lattice. And this Haldane phase has never been realized. What's realized nowadays for the quantum anomalous Hall state is a state in which you have magnetism. You have ferromagnetism from magnetic ions. That breaks time reversal. It's not a loop current. So I would still say we're still going to try to find the Haldane phase, right? Okay, but this state can be realized in a T-V1, V2 model. V1 is nearest neighbor Coulomb repulsion. V2 is the second nearest neighbor Coulomb repulsion on the Kagome lattice. I won't go into the details of that. So what is this phase now? If I'm at the Van Hoff filling, this 3Q charge density wave with loop current order goes into an insulating state, and that insulator is a Chern insulator. See, the Fermi energy now is in the band gap, and all these bands carry non-trivial Chern numbers. Right? You can count all of them, and it's a quantum anomalous Hall state. If you have only one orbital, and if the Fermi level is precisely at the Van Hoff filling. So let's ask, what if I move this Fermi level a little bit away from the Van Hoff filling? You're going to have to move your Fermi level into the band, right? Either into the electron band or into the Hall band. That's a Chern metal, right? And that's a Chern metal with some small Fermi pockets that is occupied or unoccupied states near the top of the valence band or the bottom of the conduction band. Right, so I'm going to show it explicitly here. Here is one that's above the Van Hoff filling, sort of more electrons, right? And again, in the loop current state, the Fermi energy is into the electron band, right? You have this Fermi pocket here, 6 of them. I plot all of them, and they're folded. This is the 2x2 folded zone. So they're weak because you fold them. The original one has more intensity, right? So I call them Chern pocket because they carry the Chern. Well, they're pockets of the Chern band, right? And they carry Berry curvature, non-trivial ones. If you are Hall doped, then you just cut the bottom one. It's the same physics. And the doped case can also be realized in this T-V1, V2 model. Okay, so I'm going to spend 2 transparencies talk about what's special about these loop current, these pockets, and then we'll go into more experiment. So I already said they carry concentrated Berry curvature. You can calculate the Berry curvature. The integral of this over an occupied band give you a Chern number, but if you're partially occupied, they give you a non-quantized but intrinsic anomalous Hall conductivity here. And you can convert to conductance, and it's more or less agreeing with the experiment. I mean, you should never take this quantitatively. We're just trying to say you can produce something of that magnitude. There are also orbital magnetic moments coming from the integrated curvature, right? Are these pockets seen? Well, I can't directly answer that. I can say quantum oscillations, Shubnikov, de Haas, and de Haas-Van Hoven, both have been done. And they've seen so many pockets with non-trivial Berry phase contributions. We don't know if this is one of them. More recently, my colleague Ilya Zakovich and Ricardo Coming, they did ARPES and STM together. They found these pockets at the predicted locations, but they don't know if they carry Berry curvature. They don't know if they are Chern pockets. So what's going on right now is polarized neutron scattering and circular dichroism ARPES. Both are trying to probe in momentum space whether around the pocket there are time reversal breaking signal. Okay, so what else can the pocket do? You have these pockets, then these pockets are connected by additional Q vectors. So one would ask, are there additional density wave orderings? So so these are connected by quarter G, right? So you could either have 4A0 kind of ordering or 3/4 of G. So that would be 4A0 over 3 kind of ordering. And indeed, I'll show you STM sees some 4A0 stripes in one compound, in the cesium-based one, and short-range 4A0 states in the potassium-based one. That's in the particle-hole sector. What about particle-particle sector? Now you can think about pairing in zero momentum, but boosted by this lattice, this pockets, connections between the pockets. Then you would have a pair that carries a non-zero center mass momentum, and that momentum would be 4A0 over 3 by 4A0 over 3. And this would be a pair density wave states. And indeed, STM has seen such pair density wave ordering. So I'll show you these experiments quickly. So this is in the cesium-based compound, CDW transition temperature 95. They go to 4 Kelvin. And you do Fourier transform of the topography. These are the Bragg peaks. And these 6 are the CDW peaks, right? And there are 2 more additional ones along one direction at the quarter G. And these are 4A0 ordering, right? And they come in at about, so it's this peak in the Fourier spectrum. They arise around 55 Kelvin-ish. And that breaks rotation symmetry. You can observe those in transport. So let's look at the superconducting state. This is the spectrum of the density of states in the superconductor. It's not a really BCS-like superconductor with a full gap. It's not. It looks like it has some sort of a V shape, but with finite density of states at the bottom. So this is a conductance at 5 millivolts, DIDV map. You do the Fourier transform of that. You see the Bragg peaks. Right? You see the CDW peaks. So CDW coexist with superconductivity. And you also see some stuff not very well resolved, the 4A0 thing here. But if you look closely, there are 6 more. These 6 peaks, right? There is, I didn't show you a blow up of that. It's not as sharp as the Bragg peak, but there are definitely peaks there. And they are 3/4 of the Bragg peak. So that's spatial 4A0 over 3 by 4A0 over 3 modulations. And that Q is the Q that connects these pockets. And what are these? It turns out the superconducting gap, that is the distance between these peaks, show a spatial modulation at this wave vector. The coherence peak height, that's this thing measured here. You look at its spatial distribution, that modulates with this wave vector. And also this zero bias conductance also modulates. So everything modulates with this 4A0 by 3 modulation. So we think, or they propose, this is actually a pair density wave state. And now explain why we call it a Roton. Pseudogap, let me show you the pseudogap behavior. This is over a wider range of energy. And this is 300 millikelvin, 0 Tesla. The superconducting gap is here. These other peaks are mysterious. We don't know what they are. We think these are actually peaks induced by the pair density wave order. But here you can apply a 2 Tesla that wipes out superconductivity. You see the pseudogap that's leaving behind. This is at very low energy. This is not the CDW gap. That's 50 millivolts. This is really at about 5 millivolts. Or you can switch out the field and go above TC. You still see this gap. So pseudogap is there, just like in the cuprates. All right. So now I'm going to talk more about the superconducting state. I think this is really an interesting problem, but it's very difficult to make progress. But I think it's the ultimate question about correlation and topology. So we have a Chern metal, right, or partially filled Chern band. We ask, what can happen if you cool down in temperature? What are the possible ground states, right? Gapped states, if you wish. Sure, we can have chiral spin liquid. We're still looking for that. We could have fractional Chern insulators or fractional quantum announced Hall state, which has just been observed since a couple months ago, right, in these twisted TMDs, right? And there is a third possibility that just goes to a superconducting state, and then I would argue it goes into an intrinsic chiral topological superconductor because of topology, because of the Berry curvature that's carried by this band. Right? And another way of thinking about this is you have this loop current going around, and then once you go into a superconductor, these loop currents cannot just disappear, so they would have to circulate around vortices and anti-vortices, forming a vortex-antivortex lattice, right? And that lattice is what the PDW is all about, this emergent vortex-antivortex lattice. Let me recap a little bit why we call it this way. So something is amusing when you try to dig out what has been said about it before. So let's start from a neutral superfluid. We know there is a phonon mode and there is a Roton mode, right? That's excitations of a helium-4 superfluid. Landau studied this first, and I think he coined this as a Roton because it carries non-zero angular momentum or vortices. Right? Landau believed that you quantize this and that. That's what superfluid is all about. But that's, of course, not the case. But what's really striking was in around 46, this is one of the London brothers. He says, this Roton really indicates some sort of short-range order because it says there is a very high probability for the atom to come close to be on the order of angstrom distance. So this is actually a short-range order. Right? This is really so ahead of our times. So I'm now very brave to talk about short-range order. Right? But of course, it takes Feynman to think that all of these are just collective excitations in the density-density channel, and a Roton is a tightly bound vortex-antivortex pair. Right? You have a vortex and antivortex tightly bound. So it's like those, it's like a smoke ring, right? That's a vortex-antivortex and bound together, and that can actually propagate. Right? And this can all be calculated in the density-density correlation function. In fact, I think I'm about to say that Feynman was the first to write down a pair density wave water parameter, which is right here. Okay, so this Roton physics is in fractional quantum Hall effect. Right? It's also believed by Tomo to be really the origin of this magnetic resonance mode. It's actually a magnetic Roton mode in high-DC cuprates. And if Roton, you can drag it all the way down to low energies, and if that condenses, then of course it's then we call it a Roton pair density wave state. That's where the motivation is. So can we calculate in a well-defined model and show these vortices and antivortex are all there? So that's what I'm going to do now. I talked about this Hamiltonian. I also talked about this Hamiltonian. Let me add now a superconducting pairing term, which is between mth nearest neighbor on this Kagome lattice. Right? The reason I put m nearest neighbor is because this lattice is so intricate. Different neighbors, whether it's the same sublattice or not, it behaves kind of differently. All right. So I swear this is the only thing where it's a little more technical. I'm just going to write the electron in terms of the quasi-particles in the CDW state. Right? These quasi-particles form these Chern bands. And then I pair them, and these are the pair interactions between them. Right? This is the interaction term. Right? It's actually very complicated because these things carry all the information Berry curvature. And I can actually also rephrase this as quantum geometry or quantum metric, if you want, sublattice interference and multi-orbital effects. Very complicated. But actually, it turns out the physics is very simple. I would say it's the simplest possible thing for the very reason that these pockets can be small. If these pockets are small, I'm just going to make an approximation that nothing changes around the pocket. So these are just numbers. And then you can sum out all of these indices. And this is just a 3-component superconductor, right? One here, 2, 3. And they have some pairing interaction. And that pairing interaction is a 3x3 matrix. Pair interaction and pair coupling by Josephson coupling. Right? Those are the off-diagonal terms. That allowed us to make a lot of progress So 3-component superconductor is what this ground state has to be. And what's loop current? The rule of loop current is to make this Josephson coupling complex by introducing a Josephson phase between these components that depends on the loop current and depends on the topology, because this Berry curvature will contribute to this phase as well. Okay, that's all. And now we know exactly what we can say before we even do a calculation. The leading instability is given simply by the eigenvalues of this matrix, which one is the lowest energy. Right? And in fact, without loop current, people have known this for a long time. This is just a 3-dimensional representation of the cubic group. There is a 2-dimensional one, irreducible one, which is called E2. And that's chiral. That's you take this 3, you make an angular momentum plus minus 2 arrangement. That breaks time reversal symmetry, but of course, it's Z2 time reversal equivalent. And then, unfortunately, the ground state is always boring. It's just adding these 3 together, S-wave superconductor. So there is a chiral state up there, but it's excited. You can't reach it easily. Now let's ask what happens when I have the loop current switched on. Then its phase is tunable. Then you can actually tune this so long as this phase is large enough. You're in the ground state, which are chiral, one chirality, the other chirality. Lz equals to plus 2 or minus 2. Those are the D plus ID state that I made with the electron-phonon interaction, if you wish. I don't need unconventional electron-electron interaction to produce this. Oh, sorry, I got a little carried away. What time is it? Okay, I'm going to try to speed up. And of course, the ground state turns out to be a 120-degree order. That is exactly this chiral state. Right? I'm going to show you here. This is actually an illustration of 3-component chiral state. Now, what's plotted here on sublattice 1 is the phase of one component pointing in one direction, one phase. Squint your eye, only look at the red arrow. That's one sublattice is a component of the superconductor with a phase that I call 0, pointing to the right. And the blue sublattice component will be 120-degree rotated, the phase. And the orange one is the phase of the superconductor order parameter rotated by another 120 degrees. And these are the vortices, these and anti-vortices, right? And this comes from solutions of self-consistent equations and all that now. This is the 2x2 because I have a 2x2 order, so there could be this vortex-antivortex lattice forming the 2x2 chiral structure. And this, of course, is a continuous version of this that I showed you before already. Now, here is my last punch point, is now if I freeze the order parameter, only look at the phase of the superconducting order parameter, it looks like a classical XY model on the Kagome lattice, right? And that's something that has been studied as I was introducing in the very beginning. Whether Canid order, if I go beyond the mean field theory, Canid order, that means this phase will be locked by 120 degrees. And we know it's not so easy because of these vortices, right? These chirality fluctuations. It doesn't want to order. In fact, it orders at even lower temperature than the crystallis-talus transition. So appropriate to talk about it here. It has to be lower. So this is what we worked out, that if this is your mean field transition, then the phase fluctuation will drive the true superconducting transition to much lower temperature, exposing a huge region in which there is superconducting fluctuations. And it is in this fluctuation region that one might expect higher charge superconductivity. For example, I can make now a Charge-6e object, which is product of the 3 chiral components. 3 components, 0, 120, and 240. If you add the phase together, it cancels out. It's 0 mod 2 pi. So this 6e order parameter will not couple to the chiral phases. So as the chiral phases fluctuate strongly to kill the charge 2e superconductivity, this charge 6e will be a remaining vestigial ordered state, and that's the 6e state. I have another way of showing it. Again, an exercise for everybody to try. I can write down a charge 2e order parameter BCS form, right? With these 3 order parameters having this phase difference. B is just a pair. Now, if you just expand this exponential, we all know how to do that. You expand, you see that I get linear term, one pair. This term is quadratic, so it has two phases. And the cubic term has the multiplication of these three phases, and the phi's cancel out. There's no phase coupling to here. Now let me imagine, so the 6e state decouples from chiral state. Right? BCS wave function contains all pairs, 2e, 4e, 6e, and everything. But if you write in the coherent state, it's that of the 2e. Okay? But now things can change if the chiral phases fluctuate strongly. So let's see, this average, this fluctuation kills all of these. Now the only thing surviving is this. This is a phase coherent state of 6e. Right? So that's really what I mean by there is a chance by melting the 2e I can get to the 6e. Right? How do we see the 6e? I'm going to take two more minutes. I'm going to show you the final part on the 6e. So how do we measure the 2e? 1961, Fairbank. You have a multi-connected cylinder here, pass magnetic field through, and the trapped flux, or the fluxoid, is quantized in units of the superconducting flux quantum. This is the quality of data back then. This one is a little better, 1961. Right? But in the back-to-back paper, this is the place where I find really amusing, back-to-back, 3 pages apart. It's Ziqian's paper where he explained this in terms of a superconducting, a complex order parameter on the multi-connected geometry. This order parameter has to be single-valued, therefore this kind of quantization must exist. And you can write this as the flux plus the flux screened by the supercurrent. This is called the fluxoid. It's quantized in units of this. And that leads to a velocity oscillation in units of 2e flux quantum. Free energy quantized this way, 1961. 1962, Little and Parks, they're genius. They thought, free energy oscillates, everything must oscillate. So they say Tc must oscillate. And this is Tc as a function of flux, magnetic flux. It really, truly oscillates. But it's very difficult to detect that. And they are really creative. They said, okay, let's translate this Tc oscillation into magnetoresistance oscillation. That is very easily measured. Right? So that is like this. No flux is this. Tc is high. Maximum half flux quantum, it shifts this way. So if you're looking at one temperature, the resistivity is oscillating. So put on leads, look at resistivity. It oscillates, and it has to oscillate with this periodicity. And that's indeed what they found in tin. Right? So obviously what should be done is try to do that on the Kagome lattice. Right? And this is what Wang tried. This is, in the middle, is the ring structure. Right? He wants to make with this flakes of this Kagome superconductor. Right? This is about how thick it is. It's about 15 to 20 layers. And the whole central hole area can be as large as 1 micron squared. But things do not look like little Parks oscillation at all, because you look at the transition now. It's so broad. This is resistance versus temperature. This is the zero resistance state. And this is the onside of superconductivity. Such a broad transition region. And there are features in them. That's really good news. There's some stuff going on in there. So before I show you their data, I want to convince you this device, which looks pretty crappy, right, can produce little Park oscillation. So this is you use niobium, conventional superconductor. Looks pretty ugly. You put the field on. The transition, first of all, the transition is really sharp here, right? And then you put the field and you look at just around this temperature, you see these oscillations in magnetoresistance. And the periodicity is precisely corresponding to a charge 2e flux, so long as you use this, the red triangle, a red rectangle, as the area, effective area. And this was actually shown theoretically that if you have a thick rim structure, the area you should use is in the middle. Right? This was pointed out like that. Okay, so this is my last transparency on CVS. Let's see what they observe. They see oscillations, flux, oscillation 6e oscillation, just going down from the mean field transition, then 4e, then eventually 2e, all right? So what do they see? Let me show you here. These are the oscillations, subtract background. I'm only showing you the 6e data here at the highest temperature. You take this minimum, you put on this plot, the 6e, at lower temperature become 4e. At the lowest temperature, it's 2e. All of these were obtained with the inner hole area as the effective area for calculating the flux. This is actually different from what I was just showing for the conventional superconductor. You should have used something in the wall, right? Should not be this. And this is the reason this paper is still under review. Spent a year and a half at Nature, and now it's at Physical Review X. So we're hoping that it's going to be published soon, right? So the argument is, this is you don't know if it's actually 2e, then you use a bigger area, all right? Then we say, then what about the 4e? 4e is fractional. 2e is fractional. So the reviewers are actually willing to accept fractional excitations rather than higher charge superconductivity. So then we were debating, and then Patrick Lee and Junhong Han, they wrote a paper. They say if you have such strong fluctuations, then they did a time-dependent Ginzburg-Landau calculation and showed the actual trajectory is hugging the inner hole, because once you come so close to the wall, you can't fluctuate into the hole, right? Because there's no material there. That reduces the fluctuation, and that should be the case. But that wasn't good enough to convince the referee. So eventually, Jian Wang's group made a really great sample. Look at this ring structure. It's much bigger. Now you look at the oscillations. Again, here it's 6e, and the area is this red triangle. Why do I say triangle? Red square. Now let's say, hypothetically, if these were 2e oscillations, what would be the effective area? It would be the green. All right, so that's bigger than the device. We can rule that out. So this is obviously a higher charge quantized state. So that's the end of my talk. I basically show this to you. Perhaps I'll end it with this page. That we all know Phil said this, which guides so many of us, that more is different, right? But actually, Phil had a subtitle, which I think is more to the point that I discussed today, that it's broken symmetry and the nature of the hierarchical structure of science. That's why more is different. Thank you. I apologize for dragging you.
Questions? Okay. So okay, I think Ron was first.
So this persistent current going in circles.
Yeah.
Quantum mechanics will require us to have phase coherence when you go around, right?
Yeah.
So does that mean every loop has h over e flux quantum?
H
or
over E.
For single particle?
Single particle. Yeah, these are just persistent current. Yeah.
Okay, so
So
I estimated then there's a magnetic field on the order of 2,000 Tesla.
Yeah. This is actually Brad. I think Brad knows more. We had a friend, mutual friend back then, Ted Su, actually did the calculations very small because it's staggered.
Okay.
Yeah. So if you actually calculate with this distribution of current, the flux is
so I can't just
mellingauss, something on that. Even very small.
All right. Okay. So I don't have to worry about a astronomical magnetic field there.
No. You don't need to worry. In fact, we worry it's too small. Yeah. But with this lattice strain, you can produce something. At least you can produce a uniform component, which is small but uniform. And we believe that's what this magnetometer is picking up, a torque magnetometry. They pick up a little moment, very tiny.
Leo?
Thanks for the wonderful talk.
Thank you.
If you have this loop current state, both above the superconducting transition and coexisting with the superconducting phase,
Yes.
you should see highly nonlinear transport response in the normal state, and probably really obvious superconducting diode effect.
Yeah.
Is that something that's already observed?
That's all observed. Yeah, so I think it's probably being published as we speak. So they did superconducting diode effect using a Ziqian-based compound. So that's just basically saying the critical current is actually different for current going this way or current going that way.
But
Right.
how about the nonlinear response in the normal state?
This is in the normal. You mean the time reversal breaking in the normal state? There is no. Oh, you're saying diode effect in the normal state,
Yes,
not
yes,
superconducting
nonlinear
diode.
transport.
That hasn't been done. Yeah.
Right.
Yeah, I know exactly what you're saying. Yeah, that hasn't been done.
Okay.
I don't know if it's because of technical issues, the superconducting state is better, or why not do that
Okay,
in the.
okay.
Yeah, I think
Okay,
that's a great thing to do. Actually, it should be so. So whatever energy scale where the time reversal symmetry breaking happens is way above the superconducting transition temperature. That's why these current cannot disappear. We think it has to be in the superconducting state. Otherwise, the superconductor would just expel these current together with the field. Yeah, but it's sort of the CDW energy scale is much higher. I should say, the most recent experiment finds even above the CDW transition, just above the CDW transition, they see time reversal symmetry breaking signal. So it could be actually even higher temperature. Yeah.
Yeah, thank you for that beautiful talk.
Oh, thanks.
I was wondering, since you have that Chern band, has anyone looked for a surface, chiral surface state?
Yeah, well, that's a very excellent question. Now, maybe I was, sweeping some things under the rug, but this is only one orbital, right? That I said from the very beginning, simplest possible thing. So the thing is, two reasons. One is I'm only working with one orbital. I don't really know in the true material we have such a state, right? We're really working towards understanding the material starting from the simplest possible one, right? Multi-orbital is the first thing I worry about. The second thing I'm worried about is this thing is a metal. So in the metal, these edge states are actually very fat, right? You don't have well-defined edge. So it goes into the bulk. But it certainly would have domains. And there will be states near these domain walls. But well-defined edges, they haven't seen. Yeah, probably because it's a metal. If we can drive this, many people trying to dope this into an insulator, maybe when that happens, then I think people will jump in. Yeah. But, really, we're just making small progress towards the real material. Yeah.
I think it's time for us to thank our speaker.
Oh, thank you. Thank you. Again, I'm sorry for keeping you guys here for so long. I didn't pay attention to time. How much did I overrun?
Not much.
Okay. I hope it's